We're at the end, and we're getting near the end, and you're probably feeling exhausted of the many things that you have to do. But at the same time, we've really hit some really interesting and fun science, and that's this whole idea that I want to present to you. So as I said, I'm just going to go as far as we can, do as much as we can, and see where it leads us. So here is the goal, anyways. Right today, we have done a bunch of sections in 39. I think we have done up to like section 5. And so looking closely at it, I decided that we will go ahead and continue on today until we get to section 9. I think that could go pretty fast and really hit some things that we really need to hit that didn't quite get to. And but still, then, that will lead us, then, into Chapter 40. And so I'm hoping to start Chapter 40 and maybe do some quick discussions about just what is in 40 and even cheat some of the algebra and not actually do some of the algebra as we get into section 7. All right? And so that's what I want you to write down, because that's where I know for sure we will get, if not today, certainly by Tuesday. And so you can count for sure on that is going to be on the test. I'm also thinking that we will get a little bit into 41. And so if everything works right, I will hopefully be saying the same thing on Tuesday, where I will be adding 41 on here or something. But as it stands right now, this is what I know for sure we will be doing, and something you can work towards. Also, your last assignment that you will turn in will be the Chapter 39. I got to thinking about this last time, and I want you to kind of invest your time in what you think is extremely valuable. I know you have math tests, and you have chemistry tests, and a lot going on here, as well as getting ready for the finals that are coming up. And so the last assignment to turn in is going to be the 39. Some of you have already done it. Most of you have given it a start, but 39 will be the last one. And so some of you already picked up number 40. That's fine. I would encourage all of you to at least pick it up, because we are going to talk about it, and it is going to be material that you're going to be on this half test coming up, and you're going to want to do the review for that. Oh, I should talk about the review here in just a second. I talked to Don about the date and time and all that. But anyways, and so you should look this over, and you will have to individually decide for you. Do you feel like you need to do all these problems in order to prepare for the half test, or can just kind of skimming through it get you close enough or reasonable enough, and you got to weigh that against your grade in here and your grade in your other classes. And again, hopefully we'll even touch on 41 here, but 41, again, won't have an assignment to turn in. Okay, the review. Don said it made a lot of sense, unlike the past, not to do it on Sunday, but to do it on Tuesday, so he would know where we got on Tuesday. And as you guys point out, it's also Sunday is Mother's Day. So between all that, he was shooting for Tuesday, and what he wanted me to get some feedback from you guys on that Tuesday was a time frame. Is there a math class that starts at 5? If that case, maybe he should start at 4, and then maybe people... And it starts at 5:30? See, that's good to know. So I think then we should probably start at 4 and kind of overlap, and that way some people could, if you got a class at 5:30, you could still hit an hour and 15 minutes of that, and then those of you maybe who have a class that doesn't get done till 5, then you can come after 5, and so Don can kind of overlap the two. Sound like a good plan?
Is this Sunday?
Tuesday, 4 o'clock. The only drawback to it would be we'd have to do it over in the lab room, PS 116, since there would be a class in here. Okay, but okay, plan on that, and I'll share that with Don. All right, well, back to where we left off, and see how far we can get, and maybe more importantly, is I'll just kind of skim over a lot of the algebra that I probably should have done last time, but it's kind of neat to see it. But at the same time, that's not the intent here. The intent of here is just to really get you acquainted with the relativity. Some of you will go on and take more relativity. Most of you will not. But the idea is most of you should be acquainted with the end result. That's what I want to really get accomplished, as well as be acquainted with the next step here, which is the quantum mechanics, and why there is quantum mechanics, and why we've got to deal with it. So as you know, we did that Lorentz transformation and the connection between what is the space and time by one observer versus the space and time by the other observer. So let's keep going here, because here is the interesting idea about this, and it goes all the way back to the lecture we had before the test on the idea of time dilation. You see, if time is not the same for each observer, that is the only way we can have the speed of light being the same for each observer. So without kind of repeating all that, that was Einstein's brilliance. He realized that the way we are doing our mechanics is we are all assuming that the time by each observer is the same. And if you do that, then you will have scenarios where things could go faster than the speed of light. Yet the experiments were saying doesn't seem to be the case. And so he kind of flipped that and said, well, what if the speed of the light is the same to all observers? If that's the case, then time can't be the same for each observer. And then how must time be related? And he starts there, which then led to our length contraction, which led to our Lorentz transformation equation. But it also changes everything, and that's what I want to spend the rest of the chapter talking about. What about momentum? You know, we were used to the formula that momentum equals mv, right? But of course we have a v in there, which has to do with velocity, which has to do with distance and time. But distance and time has now been altered, changed. Or I shouldn't even say that. The realization that it is different than we thought it was has to come into play. And so, as you might expect, that is not exactly right. It is incomplete. And so, just like our notion of time was incomplete, because we thought, hey, this observer and this observer measured the same amount of time, we realized they don't. There's a factor of gamma. And the gamma is close to 1 for most of the world we live in. And so we think, oh, okay, that makes sense why we thought that, because we live in a world that is slow compared to the speed of light. But as we get close to the speed of light, that's not the case. So we had a new equation to relate time. We had a new equation to relate distances. And of course, you would expect we're going to have a new equation for momentum. And you can kind of see it in the Lorentz transformation. I'm going to save time and not really derive it here, but the whole reason of going through that Lorentz transformation was that we would have to ask, what would be the equations of motion? How would mechanics be different, or maybe I should say, how mechanics should be more complete that would include high speeds? And so one of the first steps is about space and time and the view back between one reference frame and another. But the next step is momentum, and the next step is energy. And I'll start here with momentum. And so if you watched a collision, if you had two objects coming towards each other, well, maybe I should put it this way, and they would collide and they would bounce off, you would have this idea of conservation of momentum. But if you keep the formula mv, when one observer observes it and says momentum is conserved, the other observer will say, no, it is not, if you're going close to the speed of light. So that's our clue that this is not complete, this is not right. So without proof, and even your book doesn't go through this one, he tries to prove some of the other ones, but without proof, doing the Lorentz transformation, he comes up with this, and hopefully it's not too much of a surprise. He comes up with this for the formula for momentum. And that's where I want to get started today, the more complete, and at least as we understand our science today, the complete equation. And I'm sure Newton thought the same thing. Oh, this is what momentum is. But like I said, Einstein discovered yet differently. And so notice the extra factor of gamma. And then also notice that it probably doesn't surprise you that you have an m and a v with a gamma. Because again, if you're going slow compared to the speed of light, what do you get for gamma? Yeah, close to 1. And so again, what we had said is that what Newton and Newtonian physics was all about was a good approximation. It wasn't the complete story. And so now we're trying to give you a complete story, at least a complete story as we currently understand it. And who knows, there might be another Einstein in the works and change everything else too on us. All right? But that is going to be our formula. I do want to do one more thing though, because you won't see it written this way in your book. You will see it written this way. Why? Yeah, so u was the speed of the object that we had been using it. Of course, then v we had been saving for the velocity between two reference frames. In this kind of discussion, u and v are really kind of the same thing, because if I was watching the momentum, I would put, you know, the speed that I see that object moving. So I'm not sure it's all that critical that we make a difference between the u and the v, at least in this formula. But what I do want to emphasize is it did matter back here the other day, and so I just wanted to point that out, that hey, don't confuse the u and the v here. But I'm going to use the u to say this is the speed of that object as seen by me. So there really is no third reference frame to worry about, no s prime system. Yeah.
So that u you're saying is the object itself, and the v, what if it was a v?
Then again, so I don't, in this case, I'm not going to make a distinction between the v and the u. There's no point in that. We don't have three things to focus on. We made a distinction last time because there were three things to focus on. One reference frame, another reference frame, and a bird. Right? And so we needed the speed of the bird as seen by this person, but we also needed the speed of this reference frame as seen by that one. So we needed two symbols for speed. Now we don't, if we're just looking at it ourselves, we're just going to say, hey, the speed is v or the speed is u, whatever you feel more comfortable with. Okay? Now, I'll keep going. Like I said, this was no way was a derivation, but it was a way of hopefully kind of setting the tone that, hey, our equations are incomplete, right? We would have to go through and change our equation for momentum, change it for energy. And we might discover some new things along the way. And hopefully we will here along here. But you also see something for the first time. Can anything go the speed of light?
Light itself? All
right, light itself. Very good. Can anything with mass go the speed of light?
But doesn't photons have mass? Very small amount.
Photons do not have mass, no. All right, so you're beginning to see that in order to go the speed of light, what would happen here in this denominator? That's what's going to approach zero. So now, how much momentum do you need to go to the speed of light? Infinite, right? It seems kind of difficult for something to have an infinite amount of momentum, right? I mean, you get it a momentum by giving it a force over time, right? Force integrated over time would get momentum. And so again, that's why we never see anything with mass going the speed of light. Can it get closer and closer and closer? Yeah, in the sense that the momentum could go higher and higher and higher and higher and higher and higher. But we'll never get anything with mass to go the speed of light. We can just approach the speed of light. And so that is our first step. You're going to see it more so in the next step, and even more so in the step after this. Yeah.
So I heard some theoretical physics about something that's opposite of mass, something that accounts for galaxies not being as condensed as they should be. If something had that material instead of mass, would it affect that? Would it go faster than light because it had a negative number on top?
Well, it's a good question. I'll say yes to that, because that's what many scientists are talking about with, okay, what if we had negative mass, you know? But it's difficult for me to answer, because to me it's a theoretical discussion more it is than any experimental observation, because we really haven't had that. But we might. Yeah, and so then it would fit exactly what you're saying. We would have these things that are going faster than the speed of light. In fact, looking at the equations, it kind of shows it here, but you would, if I had a negative mass, I better not spend too much time here, but if I had a negative mass going this way, right, then that would, according to this, give me a momentum that is opposite to the direction it's moving. So that's kind of weird in itself, right? It's going this way, but its momentum is this direction. Which, of course, means if it hits something, it would go this way, right? But what if it was a negative mass moving on the negative direction of time? Wouldn't that just look like a positive mass? And so maybe our whole idea of mass is a bit more complicated, along with our time is a bit more complicated. And we only are seeing or realizing part of the scenario here. And so things like gravity may be simply explained of here's the Earth and here's the Moon, and the Earth shoots off a negative mass particle, hits the Moon and pulls it in. And so our gravity is really a collision of I stop. All right, but this whole particle physics idea is what you're getting down here, and so there's a lot of interesting ideas that some stronger than others there. All right, well, I'm going to keep going here because I want you to see a bunch of equations here before today's over, and I also want to get into the next chapter here. But let's look at this then, right? Let's look at force. You see, if the equation for momentum is different, and I'll put it over here, we've been so used to this. And I guess I'd cross that out too and say, again, it was a great first step. Like I said, we don't like to say Newton was wrong in any way, but we do like to point out it's not complete. And so the mechanics is more complicated than this. Of course, again, with our old formula, where'd our old formula for momentum go? You can see it really well here with our old formula. With our old formula, we would take the derivative of momentum, mv, and come up with an ma. Exactly, right? And the equation for momentum and our equation for force went hand in hand. But again, if we're going to alter the equation for momentum, which is altered because of space and time, then our equation for force has got to be altered. Now, it's not an unreasonable calculation. You could actually do this one, whereas this one would be quite involved. You could actually see this one. I mean, what if I took the derivative of gamma mv? Of course, it's a bit more complicated because gamma has a v in it as well as the v itself. And so we would have to do a product rule. I'll just pull the m out, but I guess we would have something that would say the first times the derivative of the second plus the second times the derivative of the first.
I'm changing near the speed of light as well, or?
Well, let's just say the time is, we got one observer now. Okay, so again, kind of like this discussion, we won't have two v's here. This is just as seen by me. Or maybe I should say you, because I've been referring to you guys as the S reference frame. So just as seen by me. And so I'd say, well, what is the force as seen by me? Now, again, I won't necessarily go through all the mathematics here. And like I said, this isn't too hard because it is some derivatives, but I want to point out the first and obvious one. Notice this does not come out to be MV. It doesn't even just come out to be gamma MV, which might have been your guess. It's gamma MV and this thing. And this is derivative of a square root, blah, 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 blah. So after a lot of math, you will get gamma cubed MA. Yay! And that's what I want to talk about here. So we can replace F equals MA with F equals gamma cubed MA. And of course, hopefully, hopefully this doesn't surprise you. What you are beginning to see is that what you have learned so far and what Newton had discovered is really kind of the first step. Everything where gamma is set equal to 1. And you can see if you set gamma equal to 1, what do you get? MA. And nobody realized that there was an additional prefactor in front of it until Einstein here. And it has some interesting consequences. This too goes down to our whole idea. Can anything with mass go the speed of light? And so we already saw it once in the momentum, and I think you see it also here a little bit better. You'll see it even better, I think, when it comes to energy here. But if you look closely at this, let's compare, say, the new formula for force and the old formula for force. If I just had a constant force, and again, we don't have time really to, repeat all of our mechanics here, but if we had a constant force applied to an object of mass m, then what kind of acceleration would you get? It's constant, right? And you would say an object just goes faster and faster and faster and faster. So if the acceleration was 10, you mean it would go 10 and then 20 and then 30 and then 40 and then 50, and it would just keep counting up, right? And it would keep going faster and faster. And if a long enough time occurred, it would get to, say, the speed of light and then go beyond the speed of light, according to this. But what is this one saying? What if your force is, say, a constant? You apply a constant force using this equation. What would this say about the acceleration? Right, as it goes faster and faster, what happens to this number? It gets bigger and bigger. So what happens to this number? Smaller and smaller and smaller and smaller. And so that's kind of the surprising change, I think, that even if I took an object and I just, like a rocket ship, and I had this infinite amount of fuel, and I just kept burning and kept putting the same force on that rocket ship, I would not get a constant acceleration. As I went faster and faster, I would have less and less and less and less acceleration. And in fact, as I got closer and closer and closer to the speed of light, what would eventually happen to my acceleration?
Nearly zero.
Nearly zero, right? And so this object would not ever get to the speed of light, even with a constant force. As the force just keeps applying more and more and more and more, and I don't mean the force is getting more and more, but the time is more and more here. This constant force, same burning of the rocket fuel, but now you're 90%, 99.9 times the speed of light. Your acceleration just gets less and less and less and less and less and less and less. And in the limit of all of this, your acceleration would go to zero when you got to the speed of light. So you wouldn't quite get there. Even if you could get there, you would never get past there, because then your acceleration would be zero, no matter what your force was, right? Infinite force here, infinite number there, acceleration is zero. So we're seeing right away here, we have different behavior, and we can't get to the speed of light. Yeah?
Does that equation show when you get closer to the speed of light how the mass increases?
Well, some people will do this. Some people will then say, let's call this the mass. And I'll put a little r here for the relativistic mass times A. And I think the reason they like to do that is they like to come back to this formula that they feel more comfortable with. And then they take an argument that says, no, we can't get to the speed of light because the mass gets so big. And that's fine if you feel comfortable with it, but I don't like it. I think it's a little misleading of what's really going on there. And I'm glad your author puts a big note on the side of in the margin there. He's in his little warnings of traps to fall into. He says, you know, it's just kind of an old way of thinking about it, is we would say the mass change and blah 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 blah. He goes, but that's probably not the best way to look at it, and I wholeheartedly agree here. So you won't hear me say that, but if you have heard that, it sounds like you have, and you feel more comfortable, fine. But that's what I'd call the relativistic mass, and then I'd say, okay, the mass is getting bigger. And of course, if the mass gets bigger, then your acceleration would get less as the rocket ship got faster and faster. But I prefer just to look at the factor of gamma.
But if you actually weight it, would it be heavier or not?
Well, weight is an acceleration.
Well, yeah, how do you weigh it? You weigh it by its acceleration. So again, if you come back to this formula, then you would say, yes, it is heavier. Right? And so, yeah. And the next step's going to help here too, because we're just going to even just get rid of the whole idea of mass in just a second. That was a mistake too. All right. Yeah. Yeah.
Oh, me?
Yeah, go ahead.
Does it still follow the first law of thermodynamics? Does it store energy? Because let's just say you spend like 100 billion joules or some ridiculous high number to accelerate near the speed of light. If you were to try to slow it down, will it give off 100 million joules?
Yes, and I'm glad you asked that. That's my next step. We should probably ask about kinetic energy. Right? I mean, let's face it. And this is the whole point of really what I want to tease you with. We don't have enough time. Those of you, again, some of you will take a class on this, and it's just that. It'll be a whole class. It won't be a single chapter at the end of the semester trying to cram in a bunch of ideas, and it just feels like getting it over your head. So it'll be a whole class. But again, my job here, I think, is just to kind of prime the pump here and just kind of get you to see really what it's all based upon. It's based upon the fact, again, I'll say it, is that if the speed of light is going to look the same for every observer, then time can't be the same. And if time can't be the same, distances can't be the same. And if distances can't be the same, then all of this, momentum can't be the same formula, force can't be the same formula, and something else that you might remember from your mechanics, this wonderful formula you're asking about, the kinetic energy. Guess what? Not going to be right anymore. Bummer. So we got to go back and we got to redo all of our mechanics again here, and that's why we have what we call Einsteinian Mechanics. What would happen to our mechanics? How would it be modified if we were getting close to the speed of light? And again, you can see that everything we've done has some kind of factor of gamma related to it, meaning that, of course, at slow speeds, gamma is 1, and they go back to the original equation. So what we say here is Newtonian or classical physics was our first step into understanding mechanics in the sense that we treated gamma as equal to 1. That's what happens when you treat time being the same for each observer. But the world is a bit more complicated than that, and that's what, 1905 was all about here. And so I'm going to cross that out, but I'm going to remind you where it came from. Where did it come from? Well, we did an integral of work, force integrated over distance. We replaced F with ma. There's the part we got to redo. F does not equal ma anymore. But if we go back and kind of look at what we did, we had V dV. Yeah, that'll be helpful. And then we got, if we integrated, say, from 0 to some final speed, we got the 1/2 mv squared. All right, so again, that's what you saw back in Chapter 7, back in Physics 121. We should do the same thing again. And of course, Einstein does. Says, well, okay, let's redo this. Because obviously the formula for kinetic energy must not be this. It must be something else, which would be this. All right.
You're saying that's work?
Oh, yeah, work. Maybe I should have emphasized. This is work, right? Is the integral of force over a small distance, right? And so that was our, Chapter 7 of Physics 121. The work done on this object. If you apply a force over a period of time, you will get the work done on it. And the work was equal to the change in kinetic energy. And so that was where we derived our conservation of energy back in chapter 7. So I'm suggesting we repeat that here. And so we can. There would be our integral now. Right? If we write this out, we would probably now put it's a cube, isn't it? Yeah, it's a cube. Now we would put in our 1 over the square root of 1 minus v squared over c squared. Actually, why don't I write it as a 1/2 power cubed? How's that? So I'll write that as 3/2 for my gamma. I'll put my m up here. I'll put my dv, dt, dx. And again, without doing all this beautiful math, which kind of pains me, but we save time here, is this one, we can do the same kind of setup that we did back in chapter 7 and write this as an mv dv. And down here we have a 1 minus a v squared over a c squared to a 3/2 power. And then we can integrate it from some initial to some final speed, or I'll just go 0 to some final speed, kind of like I set up here to get the 1/2 mv squared. And when we do that, of course, we might want to do a substitution here. Maybe a good u substitution would be appropriate. Oh, I shouldn't use u. That can be confusing. Ooh. So when you're in your math class, you called it a u substitution. Let me do a zeta substitution. Yeah. And for whatever reason, when we run out of u, mathematicians love to go to zeta in the Greek alphabet. All right, so we'll do a zeta. I guess 'cause it's not used for anything else. Nobody's going to confuse that. All right. So, well, anyways, you can then see that this, right, is the partial of that. And so it makes it a fairly easy integral to do, fortunately. And so dot, 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 bunch of math. What do you get for the kinetic energy? And you get gamma minus 1 mc squared. And so we are going to replace our formula for kinetic energy with that one. Now this one needs some discussion, in fact a lot of discussion, because this one isn't quite as obvious of what happens at slow speeds. Do you get 1/2 equals mv squared? You see, we did that before when gamma, at low speeds, when gamma was 1 for momentum, didn't we get mv back? And at low speeds for force, when gamma goes to 1, don't we get ma? This one just looks a little weird. What do we get when this one's at low speeds? Yeah, now if this truly is a 1, in other words, you're not moving, then yeah, you get 0 kinetic energy, which is what I would expect if something is truly not moving. But if it's moving just a hair, then this is a hair more than 1. Which in these other equations, we just kind of ignored the hair more. But we can't do that in something quite this simple because what's c squared? Huge. So when you subtract 1 from it, you need that little hair more than 1, don't you? In order to multiply it by the mc squared. But trust me, this does become 1/2 mv squared. It's probably worth mentioning it. Let's look at a quick Taylor series. And very quick in this sense, that if you looked at the 1 minus a number, and you did a Taylor series expansion, and so bunch of math, dot, 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 dot. What do you get? And so, like I said, we're going to spend the whole day cheating you out of some neat math here. But you will get something that looks like this. 1 minus n to the x plus n minus 1 x squared over 2 factorial. This is actually 1 factorial. This is 0 factorial. Minus, and maybe you can see the pattern begin to develop, n minus 1, n minus 2, x cubed over 3 factorial, dot, 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 dot. All right. Now, again, obviously, I did not prove that to you, but you guys are working with Taylor series. So go ahead and apply that Taylor series, and that's what you will get. Now, the reason I care about that is because I want to convince you that this new formula that we have for kinetic energy does reduce down to 1/2 mv squared. And so you can kind of see it in this step right there. Let me write gamma as 1 minus v squared over c squared raised to the 1/2 power. See, and that's why I was saying if I did a Taylor series on this, this would come out to be a 1 minus, there's the first one, 1 minus the power that you're raising it to. Well, in this case, it is a negative 1/2. Then times the x. Well, the x is the v squared over c squared. And the next term would be the negative 1/2 times a negative 1/2 minus 1 here over a 2 here. And then it would be a v to the 4th over c to the 4th. Now I'm going to stop there because I think you can see what's happening here. What if you are slow compared to the speed of light?
The terms don't matter.
See how each term is raised to a higher power. And if this is already pretty small, when you go to the next term and you square it, and the next term when you cube it, it's getting smaller and smaller and smaller. And so let me just ignore the rest of them and say, look, they're really small, unless you're close to the speed of light. But if you're small compared to the speed of light, this is probably a good approximation. And it's this one that is very helpful here, because remember, the equation for kinetic energy being gamma minus 1 means that if I take this gamma and I subtract 1, I get this first thing, which is 1 plus 1/2 v squared over c squared plus 3/8 v to the 4th over c to the 4th dot 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 minus 1 times mc squared. And the whole reason we needed to do a Taylor series on this one is because that one goes away, and to show anything left over, we have to go to the next term. So what's this next term going to become? What do you notice about that c squared and that c squared? And you end up with, yay, 1/2 mv squared. So maybe a little bit of surprise here, but it does reduce down at low speeds to 1/2 mv squared. I'll even take the next step. The next step would be this 3/8 m v to the 4th over c squared. And of course there would be other terms. In fact, to make it accurate, why don't you just calculate it this way? But this would be a nice additional term. And so if we get about 10% the speed of light, we're getting to the point where we don't trust that one anymore. So we add another term. And I've even seen some chemistry books, not at this level, advanced chemistry books, so you maybe haven't seen it, but I've had students who've come back and open up their chemistry book, and they said, you know, my chemistry book says the kinetic energy equals 1/2 mv squared plus 3/8 mv to the 4th c squared. And that's not at all what I remember from physics. I just remember this from physics. Where did it come from? And the reason is because that little electron, depending on what kind of atom it's on, can be going about 10% the speed of light. And so the chemists who were trying to calculate the kinetic energy knew that this would be an incomplete formula, and they wanted to add the next piece. It wasn't so close that they felt like they needed to do the next piece, or so close that they felt like they needed to do the complete one, which I don't really understand why not. But they added that extra piece of this will be the extra added kinetic energy. And so that's just the way they wrote the book, which I did think was kind of confusing, but anyways, it took some explanation. But you won't need it because you're exposed.
With the normal one, if you're within 10% of the speed of light, then your error is less than 5%, right? So 1/2 mv squared?
I think it was 0.5%.
Okay,
0.5%, right.
So,
Our gamma was 0.5%. In other words, 10% the speed of light, I believe this comes out to be 1.005. That's what I mean.
so if you add that extra term, how close can you get to the speed of light and stay in that error margin?
Oh, I guess I don't know. The question would be, how close is this to gamma mc squared? That's really what you're asking, right? So if I took this number, the correct one, put it on the bottom, let's say, and I put this one up in the numerator, and I set that to 95% accuracy, I guess I could solve for V.
Wouldn't that be 1.005? Or is it 0.05, not 0.05? You're saying,
0.5%.
well, in that case, that would have to be.
Oh yeah, sorry. Yeah. I'm confusing what you said. 5. So do you want to know how far I have to go before this is 5% off or 0.5% off? 0.5%. Okay. So then I guess it's 995. Yeah.
Okay.
Yeah. And then solve for V, which looks like a lot of algebra. Probably is. I won't do it now. But you could answer that question then. It's a good question to obviously ask. Oh, but again, in this first hour, hopefully the last hour we'll spend on relativity, and then we need to get to the next step here, is I just wanted you to see some of these crazy consequences that, maybe I should just call spooky consequences and stuff that's just different here. And so we're beginning to see that we've got to redo all of our mechanics, and we have more complete equations, okay? And so particularly this one, I think, is, like I said, the hardest one to grasp, because if you take the easy answer, just set gamma equal to 1, you get 0 kinetic energy. That's a little too extreme. So you got to do a Taylor series on it to figure out what it would come out to be. And I wanted you to see that it does, again, agree with Newton. So again, Newton was not wrong in any way. Newton is just incomplete, right? And I want to emphasize, especially those of you who don't do anything beyond this class in terms of high speeds, that you've been exposed to it, but you don't really need to worry about it if you're going to just keep everything under about 10% the speed of light. And there's, like as I said earlier, only a few cases where today's engineering throws that into case. But I think that will change with time, and this will become more and more relevant as time goes on. But here's one of the neatest things about Einstein's genius is watch this next step. Yeah.
Is that 1/2 mc squared plus a 3/8 mv part of that dot chain, or is it just?
Yeah, this is just this dot chain right there. So this was a question of, if I just took the first two terms of an infinite series, how close would it be to the real thing? And so this would be your ratio. And if you're willing to use this equation to calculate the kinetic energy, instead of this equation, the complete equation, then what speed would I get, and I would still have a number that is, 0.5% off. And so you've got a bunch of V's here and a bunch of V's there and a lot of work to solve for your V's. But it certainly can be done. And you could answer that question. What fraction of the speed of light would that be? Now watch this. As I said, I think this is probably the most amazing discovery of all of this, is this next step. And so Einstein writes this as gamma mc squared minus mc squared. In other words, we'll just do a distributive property here. So we'll take the gamma minus 1, we'll multiply it out, And if you look closely at it and move this to the other side of the equation, what does that look like? Doesn't this look like a conservation of energy equation? Doesn't it say like the energies before equal the energies after?
What does the MC squared alone represent?
But what does that MC squared represent?
Kinetic energy experienced by the person in the energy.
And for the first time in history, Einstein is the first to say, you know, maybe we're missing another form of energy. You know, had this been back in Physics 121, you would have done something like this. You would have said, oh, kinetic energy plus gravitational potential energy plus the spring's potential energy. And if we had a fluid, maybe you would put pressure and volume. If we had some thermodynamics equals total energy, right? You would have added up all the energies. And so, what is this really saying? That there's a form of energy that we've never thought about. What is mass? Just another form of stored energy. And so Einstein's approach here is to say, you know, this whole idea of space-time, you know, we used to think of it as space and time. But of course now we think of it as space-time. And if you say it fast, it even makes it more dramatic, right? And the best part of all this is, what is Einstein discovering now is there is another form of potential energy. It's called mass. We don't have mass and energy. We have mass energy. Could you change mass into energy? And for the first time in history, we've discovered what we call nuclear power, or energy stored in the terms of mass. And really, for the first time in history, we begin to understand where the sun gets all of its energy. And I'll give you some numbers here, but it was really confusing to the early scientists of how in the world the sun can give off that much energy for what appeared to be 5 billion years and what appeared to be still going for another 5 billion years. Because nobody had an answer for that. They thought it was like a big ball of hydrogen and oxygen and you're burning it. But if you did that, it would not even last 1 billion years. And yet we know the rocks on Earth are 4.5 billion years. So where in the world is the sun getting all of its energy? What is going on in a nuclear bomb and nuclear energy? And this is it. And you're probably even familiar with the equation. E equals mc squared. For whatever reason, it seems like everybody knows that equation. But very few know what the E stands for, what the M stands for. Seems like a lot of people know what the C stands for some reason. All right? And I'm sure it took Einstein at least 3 times to figure it out. Not joking, of course. But what does the C stand for here? Okay, the speed of light. You saw us kind of derive and go through Einstein's work, right? And the M stands for mass. And so, for the first time, we open up this question. Is there such a principle of conservation of matter, of mass? Well, I would even say there's not a principle of conservation of energy. There's a principle of conservation of mass energy. Mass is a form of energy. That's why your question earlier, I just kind of, you know, I don't even worry about the mass changing. It's pointless to talk about the mass anymore. Mass is just a form of energy. Here, watch. Here's what's going on in our sun. The sun takes 2 protons. And I'll kind of represent them with 2 circles colored in. And it takes a while for this process to happen, so there are other things going on, but I'll take 2 neutrons. But what I do want to point out is each proton has a mass of 1.007825. I'll call them U's. And some of you know that it stands for atomic mass units. It's a very small amount of mass. As you can imagine, a proton is very, very small. The actual mass, or mu, is 1.66 times 10 to the minus 27 kilograms. So instead of measuring things in kilograms, when they get that small, we like to go to a different unit. All right? But there's 2 of them. Now the neutron is a little heavier. It's 1.008665 atomic mass units. And if you take these 4 individual particles, 2 protons, 2 neutrons, and you weigh the 4 of them separately, you are going to get 4.032980. But yet, if we actually do this and hook them together and we weigh it,
Is that
you, yeah, thank you. We get 4.002602 atomic mass units. Now again, I'm not so interested in the numbers here as much as the concept here, but what I am saying here is, does it weigh the same when you hook it all together as when they were individual pieces? No. We've lost mass. Where did it go? Into energy. And it's this term that, like I said, is really saying that mass is, surprisingly enough, a different form of energy. And if the mass is then lost, then energy is gained. And the reverse could also be true. If you put energy into it, the energy can be converted into mass. You've seen the old Star Trek ones, right? Now, that whole beam me up to planet and back and forth is all based upon this simple idea that if I put somebody in this transporter and first of all measure where all the protons and neutrons and electrons are, and then convert all of that mass into energy, I got a big bundle of energy. Make it kind of a laser beam and shoot it down on the surface of a planet and take all that energy and reassemble it back into mass. Because there is no such thing as conservation of mass. There is no such thing as conservation of energy. There is conservation of mass energy. And so this is an indication of that. There is a slight loss in mass, and that's why after this happens, these 4 objects now weigh less, but are moving very fast because they have just changed some of their stored energy, mass, into heat. Yeah.
What is that conversion process?
Oh, we don't understand it too well. We understand quite well how to calculate it. But nobody has done it like Star Trek. We can't just come up here and take a human and convert it all. We've got to take advantage of what nature does for us. And that's all we've been able to do. And so this process is called nuclear fusion. We are putting things together. Nature does it for us in the sun. We have not been able to do this on a controlled level. We've never been able to do something as simple as, hey, just grab one proton and convert it. There obviously is something more complicated in there, and we know more than I have time to tell you now, but we don't know much of the story. But we do know this. This is how we would make a hydrogen bomb. We would take a bunch of hydrogen, slam it together, the process would make helium and release a lot of energy. And so we can do that in one big massive, well, explosion, you know. That's what happens when all that energy is released.
That tiny change in mass is not
Oh, okay, now let's look at these numbers. You're looking at this and it's a very, very small change in mass. But of course, that's only one atom. But what I really want to point out is that number right there. And so as we do some calculations here, what is this number? Speed of light. Small number, big number. The speed of light is a huge number. And if you're going to square it, it's huge again. So it really is amazingly surprising, not just the fact that mass is a form of energy, but it's a stored energy, and it doesn't take much mass to add up to be an incredible amount of energy. And we should do some calculations here, and I will, but you guys look like you have a bunch of questions. I'll go back here first.
So, if we go forward, we lose some mass in fusion. If we do fission, would we regain that mass?
Oh.
Or take two hydrogens, fuse them into helium, and then flip them apart back to hydrogen. Does hydrogen protons still have the same amount of mass as it previously did before we fused them?
Yeah, so what I would have to do, in order to take this apart, in order to take helium and convert it back into hydrogen, I would have to pump a lot of energy into it. And so, yeah, there is I think what you're going down is a conservation of mass energy. I put energy in, something that weighs this much now becomes 4 particles that weigh this much. And so my energy is converted into mass, just like the other way around. My mass is then converted into energy. And so I can go one way or the other. Now, I just want to make it a little more careful here. Nature kind of decides the rules here for us. But it turns out that somewhere about iron, anything smaller than iron, when you put it together actually weighs less. But on the other hand, things that are bigger than iron, like uranium, when you take those apart, they weigh less. So you might call this the lowest energy state, if you will. And so in this area with uranium and plutonium, which is a little easier to work with, we tear things apart, because when you tear them apart, and that's called fission, the two pieces actually weigh less, and so that mass is converted into energy. So for big atoms, we break them apart, fission, to get our energy. For little particles or small atoms, we fuse them together. Either one will release it. And what we have been able to do on a controlled level is nuclear fission. And so we do have a lot of nuclear power plants. I mean, just up the coast here, we have Diablo Canyon there and a nuclear facility. And then in the south, we have San Onofre, which I don't think is operating anymore. Yeah, and who knows if it'll ever be back up and running. But that's what they're doing in there. They are pulling, I don't know if it's uranium or plutonium what they're doing. Is it uranium? And so they're pulling uranium apart. And in the process, getting smaller pieces, and in the process, less mass, and in the process, energy, and then they use that to boil water. They use the boiling water to turn the turbines, which makes our electricity so we can play our video games. So, of course, the long-term problem with that is it's nuclear, the nuclear waste is radioactive, whereas something like this is completely harmless. So this is really what we got to, I think, figure out soon.
Is it due to nuclear fusion or like radiation bombardment from like high charged particles that builds you up beyond irons? Like any of that?
Oh, well, the higher ones would have had to been built by having a lot of energy with them.
Okay.
And so they were built in
The core of the star.
the core of the star that existed before we existed. So however many billions of years ago, we know it's more than 5 billion years, because we know our solar system about 5 billion years, but there was probably in a massive supernova explosion, there was huge amount of energies. And things like iron slammed together and started making these higher ones. And so all of these were made during that massive supernova explosion. And so we wouldn't have them if we weren't the vomit, if I can say, of a giant supernova explosion.
So it was non-elastic collisions, not fusion.
Pardon me?
It's non-elastic collisions
Yes.
between particles, not
Yeah.
fusion itself. Or is that
Well, I guess I would call that a fusion, because I'm putting them together, but it's a fusion that's absorbing energy. So an endothermic fusion, as opposed to what we probably want in our world, is an exothermic fusion. Right. Anyway, but that's why we have all these particles that we have, you know, and we wouldn't have them otherwise. Yeah.
Is that still measured in joules?
Okay, so now let's do some numbers, right? All right. Let's take a close look at this. Because the concept, I think, is amazing in itself. But I think the numbers can be just as amazing as we put some numbers in here. Because a few years ago, I bothered to look up how much energy does the United States use, the whole United States, not City College, not California, the whole United States in one day. That sounds like a lot of energy. Including what? Okay, I don't know if that'll even show up on the decimal points there. All right. And so I'm sure it's probably different, but I think this goes back to 2009. But I got 25,150 terawatt hours. Now this might be a unit that maybe you're not as quite used to. 25,150. I think you know tera. What's tera?
1,000 more than a giga.
Oh, okay, 1,000 more than a giga. I'll go with that. What's a giga? 9. So this is 10 to the 12, right? Tera and trillion, I think the two T's line up really well, so it's kind of easy to remember there. All right. And what's this? A watt. Okay, so that's a joule per second. And so you know energy is measured in power multiplied by time. Now to get it in joules, we would want watts times seconds. But big powers, they tend to do some coefficient, watts and hours. So, but I'm going to change the hour to seconds here. So we have some kind of number to work with. And can I borrow this? Thanks. It's like I forgot my calculator today here. So 25,155 times 3600 10 to the 12th, coming out to be, of course, what I really wanted just to impress upon you is this is an enormous amount of energy. Which probably isn't a surprise. I mean, you know, all the lights, all the people, all the cars, all the factories running. And that's how much energy, okay, in a day. All right. Now let's say we got all of that energy by converting mass. How much mass would we have to convert? Yeah, I guess that'd be energy divided by c squared. So I'm going to divide that by 9 times 10 to the 16. Did I do that right?
Yeah.
Okay. Right. And so it's about 1,000 kilograms, which, I mean, if I was picking up 1,000 kilograms, I would say that's a lot of mass. But what I really wanted to emphasize is compared to what the whole United States used, in a day. I mean, 1 kilogram would be, if this box up here was made out of water, that's 1 kilogram. I mean, 1,000 kilograms right there. That's the density of water. 1,000 kilograms of 1 cubic meter. So if I could take, okay, if I could take something more dense, it wouldn't be less in size, right? Right?
Where are we going to get all this water?
And I could easily convert that. All right. So, anyways, obviously, the numbers are big, and that's what I wanted to point out here, is that this, then, is the amazing new piece. E equals mc squared. And it doesn't take much mass to get an enormous amount of energy. Or the other way around, if you want to create mass, it's going to take an enormous amount of energy. I think back on that Star Trek one, it's like, okay, if you converted all the mass of a human into energy to beam them down on the planet, something goes wrong. I mean, that energy is probably enough to blow up half the planet right there. It's an amazing amount of energy.
So not every energy, like, conversion is perfect, and engines aren't totally efficient. And how efficient is like our nuclear technology right now, like in fission? Like, I know that you don't need just that many kilograms of uranium to power the entire United States for one day.
Well, okay. Like I said, we can't just pick and choose. We can't just grab a molecule of water and say, this molecule of water will probably be enough energy for our classroom today. Yay! All right, so I'm just going to put my molecule in there, and that will be good here for the day, right? And haven't got to that point. That would be the awesome step. It kind of reminds me of Back to the Future thing. When he just puts some trash in his little fusion reactor, and he's got all the energy he wants, right? And that's all you would need in this ideal world here, okay? But I think you can see it better here. What we have to do, and this is one of the most efficient ones, so that's why I picked it. But you can see it's the change here from 32 to 2 is about a 0.030, right? Out of about a 4 that I started with. So I know that's not quite a 4, but if that was a 4, that would be about 1%, and so I'm converting 1% roughly. Okay. Right. Okay.
If you convert it back to
okay. So I think a fun one to do is figuring out how much radiation hits the Earth. I mean, we know if we put our detectors up at the top of the Earth, there is about 1,300 watts per square meter of light getting to us from the sun. If we kind of assume that same energy is going in all directions for the sun, we could put in 4 pi times the radius squared. That would be where all the energy on the surface of this giant sphere where the light goes out and travels this far to the Earth. And so that is how much energy, or that's area. So that's how much power the sun gives off every second. If we wanted to know how much mass per second that is, I guess we would divide by c squared. And my 1 hour is up, so I'm going to not actually do the calculation. Which that alone is a pretty big number, but compared to the size of the sun, it is not. You would be, that's how many kilograms every second are disappearing on the sun. And so there's not a conservation of mass. There's a conservation of mass energy. Right? And so we're converting the mass of the sun into, after about 10 billion years, it was about the lifespan of our sun, so it's been around for about 5 billion, it's got about another 5 billion to go. But in all that time, the sun will consume about the mass equal to about Jupiter. And so I guess it's consumed or lost half the mass of Jupiter so far, roughly, you know. But again, I don't know if that helps because those are such big objects, you know, you're going to think that's a lot of mass. But the mass of Jupiter is nothing compared to the mass of the Sun. So it's really a small amount of mass. But like I said, it's the first time that somebody actually gave an explanation of how you could possibly get that much energy for so long from the Sun. And of course it opened a whole idea of nuclear weapons and nuclear energy. Yeah.
The fusion process is what drives the Sun. As we get to iron, it stops working in that direction. Does that mean? So how do we end up with heavier elements past iron?
Oh, yeah, the higher ones would have had energy go into them. So it's not going to happen on a simple process. It's got to happen during some kind of high energy event where it would absorb the energy. It would be an endothermic reaction. And that would be during a supernova explosion.
Okay, so like iron's really high up.
Yeah, so what's going to happen with many stars, and I'm not sure how big our Sun is to make this happen, but right now what is happening is it is fusing together hydrogen to make helium. And that's about all it's doing. Toward the end of its life, it will compress and start to get hotter, and I think it will make the next step before it dies. I think the helium will start to fuse together, 3 of them, and make carbon. And when it's all said and done, that's about as far as it can get. It won't get to high enough temperatures and pressures. Some stars are bigger than ours and will start to fuse the carbon together, and then I'm not sure what they'd make. My guess would be, you know, 2 carbons would make, I guess, a magnesium. 3 of them would make something in here or something more complicated, but it's going to stop there at iron. And so, you know, if we could convert everything in the universe to iron, we would kind of be stuck. We're at the end, and as far as we could tell, that's what's happening. The galaxies are getting farther apart, and as they're getting farther apart, they're using their energy, and their entropy is increasing, and eventually they're going to get all iron and really cold, and that's predicted, I think, like 67 billion years from now. So I guess I won't have to worry about it in my lifetime, but we know no more else. All right, well, I got to do one more, even though I'm cheating the next chapter here. Some of you will really appreciate this last one. I'll only do it conceptually. I won't even try to do some numbers. Half of you haven't even done it yet here, but I'm going to take you to this whole idea of magnetism and give you a new view. Because just like I have showed you, F equals ma is not complete. Just like I have showed you, the kinetic energy is not complete. All these wonderful things about magnetism we learned in Physics 122, or you guys will learn in 122, is not complete. And so let's take a quick look here at 2 wires carrying a current this way. Now, some of you haven't gone through Physics 122, but I will tell you, for those of you who haven't, that when we do next semester, 2 wires carrying current in the same direction pull themselves together because of a magnetic field. Okay? And so half of you have learned that, but the other half of you haven't. I'm sure all of you have played with magnets. You ever played with magnets and, you know, you feel the magnets push and pull? That's kind of what we have here. We have 2 currents where they're getting pulled together. But unfortunately, people did not know about relativity in the 1800s. Had they known it, they probably would have never even thought about this fake thing called magnetism. Fake crap. Now again, that's like F equals ma is not trying to say you should change or forget about all the wonderful stuff we learned in 122. But what it should do is open your window to something more advanced and something more complex, and certainly more complex in terms of the calculation. So don't stop doing those wonderful Ampere law calculations that we learned. They're great ideas. Carry that with you, especially you electrical engineers. But also keep this in mind. If I think about a wire which is made up of a bunch of positives and a bunch of negatives, and if I start with the idea that there's no current in them and that there's an equal number of positives and negatives, I would probably draw something like this. if I look at the forces on this wire, I would say that these positives are pushed away from the other positives. I'll label it as a force away, positive and positive. But on the other hand, these positives are attracted to those negatives. And again, if there's equal numbers of positives and negatives, those would balance. And if I just had two wires sitting there, I usually don't notice any electrical force between them. But the truth is, there's a huge amount of attraction and repulsion. They just balance each other. And we can extend that to the electrons. The electrons would see these electrons and be pushed away. So I will write that as F negative negative. In other words, the negatives in one wire, seeing the negatives in the other, get pushed away. And on this wire, I will write it as F negative positive, saying that these negatives are attracted to those positives. Now again, in a normal wire just sitting here, we say that those two forces are equal. And so if I just had two wires laying right here, I would say there's no force between them. Where the truth is, there is four forces on that wire. Two of them are attraction, two of them are repelling. They happen to balance each other, and I say, there's nothing. So what happens then when I turn on the current? And when the current starts moving, then what's going to happen is these little electrons start to travel in that direction. So the electrons travel opposite of the current. But let's take a close look at this. I'll start with the plus and plus. As the pluses look back at the pluses, nothing has really changed, and the force on them remains the same. Here's where it becomes interesting. What about this plus looking at those negatives? The pluses looking at those negatives say they're moving. And if they're moving, what happens to the distance between them? It gets smaller. And so they're more concentrated. And so the force, electrical force, is slightly increased. If I knew nothing about relativity, I'd probably invent a new force and call it magnetism. But if I knew about relativity, I would just say, oh, well, it's just length contraction. And so we don't have electric and magnetic forces. We have electromagnetic forces. We don't have energy and mass. We have mass energy. We don't have space and time. We have space-time. Exactly. Now the same thing can be done here, and we better move on here. The negatives here would see the negatives here essentially not moving, because they would just kind of be moving together, and so that wouldn't change. But these negatives, as they look at those positives, would see them kind of going that way. Well, you might say, well, aren't these going this way? Okay, but as these are moving out, they would kind of view these positives as moving up. And as they're moving up, those positives would be closer together, and that would make a small increase in force. And so I claim that this whole idea of magnetism was humans' lack of understanding of relativity and length contraction, and that what really happens in magnetism is there's a slight change in the electrical force. And these electrical forces are so big that a small change in electrical forces is noticeable. And so it was noticed way, way before anybody had any thought or idea of relativity. And so, for better or worse, and I do think it's better. I mean, people have debated this for years. Should we stop teaching physics the way we do, and where we teach everybody space and time, and then tell them later on it's space-time, and then we teach them electricity and magnetism, and then tell them it's electromagnetism? But I think it's just too much to bite in one time. You don't give a newborn a cheeseburger. But it takes a little milk first, and then a French fry, and then the cheeseburger. And so you gotta build up to the bigger stuff here. And so that's where we are, and that's where we're coming to an end. And it's always a sad we come to an end here. And many of you, half of you, will move on to bigger and better things, and good, we're proud of that. And makes me sad. We'll miss you. Although I do think it would be sadder if you failed the class and had to take it again and again and again. So I am glad that many of you are moving on. All right, well, as I said, I wanted to do that in the first hour. Obviously, I went longer. Let's continue on here. All right? Let's begin to change topics here. Let me start with this picture. I'll call this the start of chapter 40. Let's look at some other interesting things. And maybe the way to graph it here is maybe if I put a vertical axis called size and a horizontal axis called speed, which is really weird for your coordinate system. So this is not space and time or energy and time or anything like that. It's more of a diagram that I can go ahead and draw a solid line here and call that c, the speed of light. And our argument is that everything we understand about the world, we could maybe hypothesize that there's something over here. But everything we know for sure from experiment is on this side of this graph. It is going less than the speed of light. If it is light, it's here going the speed of light. If it's anything that has mass, it's over here. And most of the world that we're familiar with is way over here. And so I will kind of divide this in half and say we have mostly done slow moving objects. This is where Newton's law, classical physics, Newtonian Galilean physics, right? This is the stuff where we have spent the 3 semesters mostly together, except for this last chapter. This last chapter, we kind of crossed the bridge, or this dotted line in this case, and said, what would happen if we went closer to the speed of light? And what we found here is that there's got to be modifications to what we have discovered. And fortunately, Einstein did a great job in the sense that it wasn't just a partial discovery. I mean, he found everything up to the speed of light, right? And of course, his equations would also be valid all the way down here. But as I was trying to say here, is the equations and the ideas are so much more difficult that we'll use F equals ma just fine here. But when we transverse this little position here at 10% the speed of light, we will change from things like F equals ma to F equals gamma cubed ma. Well, I wish that was all we had to do. Because again, starting here in about 1900, starting with Planck, this is where we'll get started in chapter 40, we as humans and as scientists have been able to probe things smaller and smaller and smaller. And so that's why I put size on this axis. And I'll put about the size of the atom here. And Newton's laws seem to work great, as long as we were bigger than the atom. And so as we got smaller, it didn't work either. And not that we were going faster. So for totally different reasons, it was just incomplete there too. And so what we will see is we will get the discovery of a mini people. Mini people. And we will call this quantum mechanics. A key player here is Schrodinger. There are many others, so we don't call this like Schrodinger's mechanics. We call it a quantum mechanics. But I want to... Oh, yeah. I just ran out of space there. But again, in what's often referred to today as the 30 years that shocked physics, was we were finally getting to the point that we can go both faster and smaller, and we were seeing there is just something seriously wrong with what we call the old theory now. It just doesn't work. There's obviously more to the world than the kind of science you have been exposed to so far. And this chapter, 39, we just wrapped up, did our best to kind of expose you to that. And these next few chapters, in the half hour we have now, plus the 2 hours we have together on Tuesday, we'll talk as much as we can about this one too. But I just really like this graph because it really shows the two separate pieces. Things that are small, you got to think a little different than we've been doing. Things that are fast, we got to think a little different than we've been doing. And it shows it well. And of course, maybe for completeness, I ought to put some of the work done by Dirac. But Dirac kind of takes the two together eventually and says, well, what if we have small things going really fast? And we won't even touch on that here in this class here, but it needs to be addressed. What would the equations look like then? And so we call this Dirac and Dirac mechanics. Yeah. But I should emphasize we're not going to touch this box.
What happens when math gets really hard?
Yes, the math does get very hard. That's true. But without even trying to answer that, let me throw a third axis on here. What about accelerations? What if the things are really small, going really fast, and being accelerated, like, say, in the Big Bang or near a black hole? How do they behave there?
We don't know.
We have no idea. But that's why it's such a great field for you guys, right? There is what Feynman used to love to say, there is plenty of room at the bottom. Nanotechnology, and things that are small, and things that go fast, and things near the black hole, we're just kind of clueless. We've got a lot of science to discover here. And so the world is big and wide open on all kinds of opportunities. And of course, in the next 30 years, I mean, everything's going to be smaller and smaller in nanotechnology. And the things that people will do will be absolutely amazing. And people will try to understand how it is trying to do. And if you only understand this science, it's just going to be impossible to explain it to somebody. You know, well, how does that transistor work? Well, I can't use anything from here to explain it to you. So I got to do this. And so who knows? Maybe we'll start teaching this in junior high. I don't know. You know, so. But like I said, I think it was your class earlier, remember? Or maybe it was the other classes. I mean, we're only 1900s and got a lot to learn, but you know far more than Newton did, right? Newton was stuck in this box, right? And his math was just Calc 1, you know? And so, yeah, well, long way to go. All right, well, what I'm going to start off with, and hopefully go kind of quickly here, is the starting point of quantum mechanics, kind of like we did with relativity. My starting point with relativity was, hey, let's think about some experiments that were done. Let's think about what we would have thought would have happened, should have happened, but yet didn't happen. And if we can figure out how to explain it, maybe that's a better answer for how the world works. And so your author starts off with 3 experiments here, and I want to do the one here. It is called the thermal radiation, as you saw it earlier. In this chapter, they'll refer to it as the black body radiation. And what it means by that is just take an object that gives off light, and it doesn't even have to be visible light. You just have a temperature. You learned this back in our thermodynamics as Stefan's law. Now, we didn't do much with it because we said that we would revisit it. Well, here we are. We're revisiting it. Remember, there were 3 ways to transfer energy from object 1 to object 2. What were they?
Radiation, convection.
Yeah, conduction and convection, and then radiation. And what radiation is, these light waves, these electromagnetic waves going from one to another. So we would say that we get our energy from the sun. Not by conduction, not by convection. Those all take molecules. How do we get our energy? By radiation. Electromagnetic radiation. And so our energy comes to us from the sun. You too, as a human, as a person, this desktop gives off radiation. And what we learned was a measurement by Stefan, no explanation, But what he noticed is that the amount of power given off, the amount of energy given off, had to do with its temperature. Does this kind of look familiar? All right. And of course, all these other terms, maybe I should put back in here. This was referred to as Stefan's constant. And like I said, we didn't really use it because we were kind of waiting for this point. So we can kind of understand it a little better. But it was more of a measurement of how much energy is given off by an object at a certain temperature. What I want to do is maybe take a little bit more of the experimental data and emphasize this. Oh, maybe I'll put it under here. Oh, I'll put it up here. The early scientists in the late 1800s were measuring this, and they were measuring, okay, how much energy is coming from an object. And so they would heat an object. Let's take a simple one, and you heat it at about 2,000 degrees. And you plot how much intensity do you get at different temperatures. And I'll put a little drawing up here to emphasize this is their measurement, not a calculation, no explanation, just this is what you get. You go in, you take a piece of tungsten, you heat it up to 2,000 degrees, and you say, well, what do I get? And they notice it peaks then at some wavelength. 2,000 degrees isn't that warm. It's probably getting close to the infrared, probably at that point where it peaks. There might be some small wavelengths down here in the visible here. Remember, this is wavelength, so small wavelengths would be here. So if this is infrared, visible would be over here somewhere. All right. So maybe we would start to see this piece of metal kind of glow red, and we might say, okay, it's getting red hot. We've heated it warm enough that it's starting to give off ones that are visible. If it was cooler than that, at about 1,000 degrees, it would probably be much smaller. But I want to go the other direction. Let's say we warm it up again. All right, so we go from 2,000, and I'll just change colors here, to maybe 3,000. And it gives off more energy. Now, it should. This is the observation, right? The higher temperature means it should give off more energy. And so the total energy it gives off would be the integral, right? It would be the area under this curve. This is the power for a given wavelength, and so all the energy would be this integral. All right. And now let's warm it even more. Let's go to 4,000. And I'll put a 4,000. But again, I want to emphasize this is not any kind of graph that is explaining anything. This graph is purely, let's go to the lab and make a measurement. Because there's a very famous calculation that comes out wrong. That was done by Riley and Jens. And they said, we should be able to calculate this. We know our electromagnetic theory really well. We know our statistics really well. We could just take a bunch of BBs. Here's our BBs. We can heat it up. We should calculate what frequencies they should give us. And if we should get 2,000 degrees, then we warm it up to 3,000 degrees. Then we warm it up to 4,000 degrees. We should be able to calculate this pattern. So they did, at least to the best of their ability. And they came up with an equation that I guess I kind of hesitate to even put up here, because it is wrong. Oh, and maybe I should remind you of a couple symbols. C, that's the speed of light. Okay, you know that one, I think. Do you remember this one? Okay, good. Boltzmann's constant. Okay, I won't bother to put it. T for temperature and wavelength. So this is what they come up with. So let's apply it on this graph to 4,000 degrees. And what they got, maybe I'll put it in black here, was excitement at the beginning. Because after all of their hard work, their theoretical calculation worked really well for the long wavelengths. But it didn't hook around and back down and did not match the short wavelengths. What they coined as an ultraviolet catastrophe. Meaning that if their equation was correct, you would have so much ultraviolet light that you would have an infinite amount of power, and we know that's not happening. So I'm sure, like, you would have thought, well, I must have done the calculation, or my partner did the calculation wrong, right? And so they probably tried it again and again and again. But the reason I bring this up is they eventually convinced themselves and everybody else that, no, they weren't doing a calculation wrong. Just like relativity, and actually this predates relativity, is that perhaps what's going on here is there's more to the world than we understand. I mean, the reason our calculations come out wrong is because we're so busy applying the electromagnetics, what I'll call classical electromagnetics, together with our classical mechanics. And we're getting the wrong answer. We're getting the wrong answer because something else is happening on this small scale where the light is coming from these atoms. And so, fortunately, in 1900, a guy named Planck comes along and he looks a little closer at it. And as he looks at it, he says, well, I understand my stats really well. And he had been doing a lot of statistics on what we would call quantum statistics, meaning we're looking at one person and two persons and three persons, not a half a person. And these guys had done all their work, like the molecules can move at any speed they want. And so Planck just says, you know what? If you make this assumption, and I think the best part in the story is Planck in no way believed this. He just says, you know what? If the molecules can have only discrete, or what we're going to call quantized units of energy. What today we refer to as the first step or the birth of quantum mechanics or the quantum theory. And like I said, he himself was not really trying to explain it. Hopefully we will get to that even today, maybe. At least somewhat. But he was just trying to say, what if these were packaged in quantized energies? Meaning this, that if I were to plot energy on the vertical axis, and the molecules can't just have any old frequency they want, or any old energy they want. They can have this amount, or they can have this amount, or they can have this amount, or they can have this amount. It's kind of like going up a staircase. If you went up a staircase, and the condition is you have to stand on one or another stair, How high are you? Okay, well, I have a lot of options, right? But one thing I know for sure is it's quantized. You're either on the first or the second or the third or the fourth or the fifth. You can't be part way up. And so that's what his assumption was. His assumption was, well, let's just say that could happen. The best part about it is if you assume that and redo your statistics, which obviously we're not doing the actual calculation, you get this to curve down around and match it perfect. And Planck knew that's what would come out. So he doesn't really explain anything about why this does. He just says, if we call this step number 1, and this number 2, and this number 3, and this number 4, and you say the energy that this molecule has is some constant times the frequency, and so this one is twice that, and this one is 3 times that, and this one is 4 times that. And so that's what I mean by that word, quantized. Again, no explanation here, just what if that is the condition? Kind of like Einstein. Einstein said, look, we're just going to say the speed of light is the same for every observer. End of story. We'll just assume that and see what that leads to. He's going to say the same thing here. I'm not going to explain why this has to be true. De Broglie will in a minute here, and we'll get a better answer for that. But if that is true, we should redo these statistics. So instead of getting an equation that looks like this, where it is based on wavelength and temperature, and we put 4,000 degrees and we get it to go up there, Planck comes up with an equation that is much different because of the quantum nature of the requirement here. And he comes up with this equation. Not a simple equation. And certainly not a simple process of how the heck he came up with it. And so I'm not going to worry too much about that, but I am going to say that if you were to plot this, I'll put the minus sign a little better, minus 1. If you were to put that on a piece of paper and plot it at 4,000 degrees, or 3,000, or 2,000, it exactly matches there. And so that's experiment number 1. That is what I say is the birth of quantum mechanics. And like I said, not really believing it himself, not even given a reason, just throwing it out there for the world to think about and say, if we assume that the energy is quantized, I get an interesting result. And in fact, let's look even more careful at this result. It shows a couple of other interesting things. That is also true. Yeah.
Is that either the HC over that? Does that come from the Laplace transform of
I don't think so. It shows up in your statistical probability theory. Yeah, which I don't think, I mean, we don't teach that class here. A calculus level statistics class is not.
The way it's quantized kind of looks like a heaviside function, like a series of heaviside functions.
Yeah, it does. So now maybe, but I could be. I don't know. Yeah, I don't know. Yeah, I don't. Did I take another question? No? Yeah?
Is that the Boltzmann constant being put up to the power of t, or is this multiplied by t?
No, all this is up in the exponent of the natural log.
No, is the Boltzmann constant, the k to the b times t, or the t to the
Oh, no, it's yeah, these are all this is times t. Yeah, I just tried to make it fit. So lambda k b t, how's that? Uh-oh, what was up there? HC? HC, how's that? All right. Now, again, I'll do you a disservice if I spend too much time on that equation or even the derivation of the equation. That's not the point here. The point is that for the first time in history, somebody's throwing something out there that explains something that wasn't being explained, not even really trying to say this is true or not. In fact, he himself is even saying, this is not even possibly to be true, but hey, look what I get. In fact, it gets even better, because what if you then integrate this for all wavelengths from 0 to infinity of this equation? Now again, in no way am I going to do the integral for you, but, oh, and I erased it, but wouldn't that give you all of the energy under this curve? And after you do this long integral, you come up with t to the 4th power. Ooh. Looking a little better, huh? So not only did this assumption first explain the shape, but it also explains Stefan's law. And in fact, it does one better here. What if you were to take the derivative of this function and set it equal to 0? What does that give you? Yeah, that gives you where the function reaches a peak, right? And again, if you would go through all this math, you would come up with this peak wavelength, I'll call it the maximum wavelength, multiplied by the temperature equals a constant number. And if you go back and look carefully at the data, that's exactly what's going to happen here. Is as the temperature gets higher and higher and higher, the peak wavelength goes down and down and down. In fact, this was experimentally done by Wien, so we refer to this as Wien's displacement law. But what I'm trying to emphasize is it plays a neat part in history, because it was for the first time where somebody said, although not believing it, what if? We know we're not getting the right results for what we're currently doing. So what should we be doing? And that will lead Einstein into his next step. Einstein will say, maybe this isn't so crazy. Planck did it first in 1900. In 1905, Einstein grabs a hold of it, and besides doing the last chapter on relativity, he uses this explanation to explain the second weird experiment that nobody had a good knowledge of, which he eventually got the Nobel Prize for, called the photoelectric effect. Which that in itself is an interesting story, because I think, and probably most people think he should have got it for relativity, but it was so bizarre that there was no real experimental evidence and yet at that time, and nobody was really ready to jump on board, and nobody wanted to give a Nobel Prize to something that was that weird and would turn out to be wrong later anyways. But everybody was beginning to say, well, sure, we got to give it to him. Anyway, so I think their cop-out was kind of this, that say, this alone is Nobel Prize worthy, so why don't we give him for that? Because we know that's right. We have done the experiments. In fact, this is your experiment next week. You will repeat these experiments, and you will do the photoelectric effect here. And repeat Einstein's work. And that Nobel Prize is a lot of money. Although he never got it. That's a whole other story too. So that was part of his divorce settlement. Divorce settlement said his ex-wife would get it if he ever won. And so he won. She got the money. Maybe that was the argument, that she had helped him go through. I don't know what the divorce settlement reasoning was, but she definitely helped him go through school. And he was a real good physicist, but he had troubles with a lot of the math. He couldn't have done the math without his wife and his good friends working on the math for him. And so, team effort. Yeah. And so some people are stronger in the math, some people are stronger in the physics, some, you know. All right, but anyways, what is the photoelectric effect? So here is the second experiment. And like I said, this first part of the chapter, which I hopefully I'll get to, maybe just barely make it here, shows three really interesting classical experiments that really open the door to quantum mechanics. And like I said, this is the first one. This is the first one that we actually get an explanation of what's going on if we're willing to accept that the energy is quantized. And the same thing happens in the photoelectric effect. What is the photoelectric effect? Well, if you take a piece of metal, as you may or may not know, depending on how far you've gone in your chemistry and your physics 122 here, the whole thing is filled with electrons. And if we send in some light, that light will then hit the metal, get absorbed, and an electron will come out. And hence why it's called the photoelectric effect. All right. And it comes off. In fact, you've probably used this more times than you've ever realized. Every time you use your laser printer or you use your photocopier, you are using the photoelectric effect. A photocopier or a laser printer kind of works along this lines. I'll draw it as a rectangle, although it's probably a drum that rolls. And the idea is to put a bunch of electrons on the surface of some material. A lot of these like to use a cesium here. But with all this charge on there, if you were to flash light at it, and so you've probably noticed that when you use a photocopier, it does make a flash of light, or a stream of light goes across as it scans there. And if you were to shine light here and shine light here, you would kick the electrons off, and there would no longer be electrons there. So wherever you shine light on it, you lose electrons. So you only have electrons left where no light hit it. Well, that's great, because if I'm making a photocopy of a piece of paper, I put it face down, flash a light. The light reflects off the white stuff, but doesn't off the black writing. And if I shine that back onto my cesium here, what I will be left with is the electrons only remain in the same pattern that there was writing on my original piece of paper, where it absorbed the light, because the rest of it flashed a light onto it. And so the electrons are left only where there's writing, which is wonderful, because electrons are negative and attract little dust pieces. So I could take black pieces of plastic, grind it up into a fine, fine powder, call it toner, sprinkle it on here. The toner would adhere to here, adhere and adhere, but not here and not here. And then I can take a clean piece of paper, lay it on top, press it, warm it, melt these into the paper, and I now have black plastic melted into the paper in the shape of the original black lining, writing on my original piece of paper. And so there's your photoelectric effect in use very quickly as you flash the light and then warm it. And you've probably noticed that as the piece of paper comes out, it's warm, because it has been pressed and melted the toner on there. What they call the fuser has melted all that together. All right, that's the photoelectric effect. Now, nobody had a good explanation for it, because here's what you would have expected. If light is this wave coming in here, you would have expected a bunch of things that didn't happen. And we got a bunch of other things that did happen. For example, if you were to shine light on here, and as you send it down, if the light was brighter. Now, what do you mean by brighter? More intensity, right? More amplitude, right? You would have expected that the brighter this light is, the more it would shake that electron, and the more it would make that electron go faster. So bright light should have made this electron come out fast, and dim light should have made it come out slow. Fair enough? That's not what happened. What ended up happening is they all came out at the same speed. There wasn't some faster and slower, regardless of the intensity of light. What happened is when you turned up the intensity, more electrons came. Not that the electrons came out faster, but more electrons came out. And it was Einstein's brilliance, that and some other things that are in the same one, that said, well, wait a minute. Isn't that really an explanation that would say light is not a wave but a particle? I mean, think about it. If light is a particle, what do you mean by more intensity? More photons, more particles. And it's each particle that hits it that kicks out the electrons. And so if this light coming in, like I said, is a particle and not a wave, you expect more electrons to come out, but each of them to come out with the same speed. So light isn't a wave, is it? It's a particle. But wait, I thought we just did Young's double slit experiment. So is the light a particle or is the light a wave? Right, and you guys have already been exposed to this. Like I said, your author actually started in chapter 35 on a very hard subject when he started off and said, let's look at the nature of light. And he goes right at the beginning and said, let's call them both. Let's call them both particles and waves. And I really think you can't get a good grasp of thinking of them as particles in the experiments that we've seen so far, because we've done a lot of interference. And we've done a lot of experiments, including the one this week that some of you will do this afternoon, that clearly shows the wave nature. We see the interference patterns. But this one, this experiment, is one that clearly shows the particle of the waves. And so Einstein is saying, light is more complicated than that. This is our explanation. Light is not a wave. Light can also be viewed as a particle. And as you guys heard me say, I like that word wavicle. It depends on the experiment you do. As I said before, are you a student or are you an employee? That depends on the experiment, right? And so the experiments that we've been doing for the last chapters of our optics had been ones that had demonstrated light is a wave. And Einstein comes along and says, this experiment shows the wave nature. In fact, one better here. As I said, you would have expected, if it was a wave, that they would come off at faster speeds with more intensity, and they don't. But there's something really interesting here that really ties it together with Planck's work. Is what happens when you start changing the frequency?
Only certain ones fly off.
When you start changing the frequency, the speed at which they fly off goes down and down and down. Why? Well, if Planck is right, Planck is saying that the molecules can only have this discrete set of energy based on this constant h. And so Planck says that the molecules can only have that energy. So Einstein runs with that and says, if that is true, that means when the molecule was at a higher level and went to a lower level, when it lost its energy, that's what created the photon. So how much energy would the photon have? HF. See, if the molecule was up here in what we will call quantum state number 4 and moved down here to quantum state number 3, it lost energy. It made a photon. How much energy does that photon have? HF. And so Einstein says that these photons have an energy of HF. That's the important step. And I think we saw that in chapter 39, didn't we? No? We didn't do much with it, so if you don't remember, I completely understand here. But
it was like the first equation, and it was either
Yeah.
38 or 39.
yeah, 35, way back in 35, very first equation. Yeah, and we didn't do much with it. In fact, they gave you the value of H. I should probably finish today by just kind of giving the value of H. Well, what is it? But it's this experiment that measures it. It's the experiment you will do next week. You will measure Planck's constant. It must be a small number because nobody's ever noticed it before, right? And so it is very small. 6.63 times 10 to the minus 34 joules second. But I'll leave you with this in the last second here, is this is the second experiment that really crystallizes and confirms that maybe Planck was right, that maybe these little packets of light are just that. They come quantized. They come like particles as well as waves. And so Einstein says this. Let's say it takes a certain amount of energy to free that electron. That electron is held to the metal with what he calls the work function. So if you think of this as a particle coming in and not as a wave, then when this particle could come in, one particle coming in, one photon, will create one electron. And its speed would be this. Here's the energy coming in. Where does that energy go? The first part of the energy has to break it free. Whatever energy is left over gives it its kinetic energy. And of course, we're not talking about relativistic, so I didn't use gamma minus 1 mc squared. So not worried about that, going back to slower speeds. But this is what Einstein said should be happening. This would explain it, that totally matched the experiment. That is, what if you're below a certain frequency? If you're below a certain frequency, what will happen? You won't kick any off. Below a certain frequency, you don't have enough to break the bond. But if you think of these as waves, a wave can make it slosh, and the energy can build up. And if you think of these as a wave model, you should get electrons that come off after a long period of time, and that's not what happened. Even at low frequencies, at a long period of time, they don't come off. They matched a particle model, a quantized particle. Well, like I said, I'll stop there. There's a third one we better talk about, and then some other things. But we'll have 2 hours for that.